This is a reassessment video for work energy. The question that I came up with says that Blake wrestles a 200-kilogram black bear away from a picnicking family. Attempting to drive the beast into a nearby ravine, he pushes the bear with a force of 2,100 newtons at an angle of 35 degrees below the horizontal. The coefficient of frictional force on the bear is 0.23. He moves the bear a horizontal distance of 15 meters with an initial speed of 8 meters per second. A. Using the coefficient of friction, determine the total force of friction on the bear. B. What is the kinetic friction of the bear after Blake pushes it a distance of 15 meters? And C. Determine the velocity of the bear after it has been pushed 15 meters. And so the sketch that I did is right here. And so we have our frictional force going against to the left, and then this is the force that Blake applied to push the bear downwards. This is 2,100 newtons, and this is at an angle of 30 degrees from the horizontal right here. And delta R is the distance the bear was pushed, which we know to be 15 meters. We also know the gravity is the mass times 9.8 meters per second squared, and then that's also going to be equal to our normal force. So that's going to help us find out our frictional force in part A. So we were given our coefficient of frictional force is 0.23, and the equation we need to use to find frictional force, I wrote it as F sub F, equals the coefficient of frictional force times the normal force. And so we can put in our 0.23 right here, but we need to know our normal force, which, as I stated before, it's going to be the same magnitude as the gravitational force downward. And it comes out to 1960 newtons. We plug this in and come out to a frictional force of 450.8 newtons. Part B says that we want to, what is the kinetic friction of the bear? What is the kinetic energy? So the change in kinetic energy we need to know is equal to the work done by the applied force plus the work done by the frictional force. And so if our work done this way plus our work done this way is gonna be the change in kinetic energy, and that is gonna account for all the total work that happens. And so our work applied equation is going to be the force applied, which we know is Blake pushes the bear with 2,100 newtons. The distance he pushes, which is 15 meters, and it's going to be cosine the angle, and it's the angle from the horizontal. So if this is our applied force, then it's 30 degrees right here until the horizontal. So it's going to be cosine 35, because that was our angle. And come out to about 25,803.3 joules. Now for the frictional force, it's going to be this is the work caused by the frictional force. It's going to be the force in newtons, which we found to be 450.8. And it's again going to be our distance, delta R, 15 meters. And then cosine theta, but it is, again, it's the angle of the frictional force from the horizontal, and as you can see, it is on the horizontal, so it is at 180 degrees. And so we're going to put 180 right here and use cosine again, and in this case it makes it a negative 6,762 joules. And joules we want because that is going to be energy. And so we know that from our equation before that our kinetic energy is going to be our applied work plus our work done by friction. and it comes out to be 19,041.3 joules. Now part C says final velocity of the bear. So we know that our work equals our change in kinetic energy. We also know that kinetic energy is defined by this equation, 1/2 the mass times the velocity squared. So intuitively we can say that the change in this kinetic energy is going to be the final of the 1/2 times the mass and the velocity squared minus the initial of said equation. And so finally at the end it said we have a velocity of initially we have a velocity of 1 meter per second, and we know that our mass didn't change. The bear is still 200 kilograms. We're going to plug this in here, and we're going to solve for our final velocity. And so now that we have this equation for delta K that helps us to find the bear's final velocity, we can set it equal to what we found our total work to be, which in our case we found out that our total work was 19,041.3 joules. We set it equal to this equation, and we solve for the final velocity. And it's going to come out to approximately 13.84 meters per second. And this is the unit of measurement that we want. So a good way is to keep track of all your units, and if they cancel out properly, then you know you're doing it right.